In this video, I'm going to show you three ways of constructing a regular pentagon. Uh, the first is the current day construction using tools that should be familiar to everyone with a good high school background in algebra and trigonometry. The second one is a classic and very clever construction from the late 19th century. And the third one is Euclid's construction, which will turn out to be by far the most complicated of the three. I'm also going to experiment with annotating my slides as I go using PDF Annotator and my tablet. We'll see how that works out. So here is a way of turning the pentagon construction problem into a quadratic equation. This approach is nice because it generalizes to regular polygons with a larger number of sides, and you'll see this used again for a construction of the heptagon. Here's a regular pentagon, and here I want a hand between this side and this side. There is an angle which is clearly 1/5 of 360 degrees, or 72 degrees. If we can construct the sine or cosine of that angle, the pentagon construction problem is solved. So let's go at it using trigonometric identities. An obvious one that comes to mind is if I multiply this angle by 5, I get a 360-degree angle whose sine is 0, or alternatively, whose cosine is 1. Alternatively, I can say if I take 4 times this angle, then I have the same value of the cosine as for cosine theta, but I have the opposite value of the sine. So here are two alternatives that involve trig functions of 4 theta. Slightly better, you can say if you take 2 theta and 3 theta, you get two vertices of the pentagon that have equal x-coordinates and equal but opposite y-coordinates. In other words, sine 3 theta plus sine 2 theta is 0, or cos 3 theta minus cos 2 theta equals 0. By using trig identities, we can compute any of these functions of theta in terms of powers of cosine theta. And if I set that equal to x, I've converted it into a polynomial equation. In each case, for all of these angles, theta equals 0 is a solution. So the polynomial equation that we'll get is actually 1 degree higher than the one we need to solve because we already know one root and just have to determine the other roots. Okay, let's go at this with standard trig identities. I hope you remember that the cosine of 2 theta is 2 cosine squared theta minus 1. I've never managed to memorize the cosine of 3 theta. I just work it out from scratch. It's cos 2 theta, cos theta, minus sine 2 theta, sine theta. Okay, first term, I take cosine 2 theta and I multiply it by cosine theta. That gives me these two terms. This one is a little less obvious. Sine 2 theta is 2 sine theta cosine theta. So this product is 2 times cosine theta times sine squared theta, and I replace sine squared theta by 1 minus cosine squared theta. And when I combine all the terms, I get the formula for cosine of 3 theta. So now I can set cosine 3 theta equal to cosine 2 theta, and when I collect all the terms, here's the cubic equation that I get. But as I already pointed out, one solution to this is theta equals 0, cosine theta equals 1. So this has a factor cosine theta minus 1. I pull that out, and I get 4 cos squared theta plus 2 cosine theta. Sorry, that's a typo I missed. Minus 1 equals 0. I set x equal to cosine theta, divide through by 4 to make the coefficient of x squared equal to 1, and I get the equation x squared plus 1/2 x minus 1/4 equals 0. If I can construct the roots of that quadratic equation geometrically, I can construct a pentagon. So here is a modified version of the approach to solving the quadratic equation that's presented in a lovely book by Bold called Famous Problems in Geometry and How to Solve Them. I'm going to write my generic quadratic equation as x squared minus bx plus c equals 0, and I'm only going to consider the case where this equation has two real roots. In other words, where b squared minus 4ac is greater than 0. B in this case is the sum of the two roots of the equation, and c, of course, is the product of the two roots of the equation. What I want to do is to construct x1 and x2 by drawing a circle that cuts the x-axis at those two roots. Now it takes 3 points to determine a circle, so I'm going to add a third point. I want my circle to go through the point where x is equal to 0 and y is equal to 1. Now we've got to do a little bit of clever geometry on this. I'm going to select pen and hope that I can draw with my nice little stylus. Yep, there's the little dot I was looking for. So let's start labeling some points. That is the average of the two roots. So it's x1 over 2 plus x2 over 2. Over here underneath p, we clearly have x1 over 2. If I look at this line, I can see that y changes by 1 while x changes by x1. So the slope of that line is equal to 1 over x1. If I look at this line, well, it's the perpendicular bisector of the segment that it intersects at P, and therefore its slope is the reciprocal of 1 over x1. So for this line, the slope is equal to x1. And now we're pretty much set, because if the slope of the line joining P to O is x1, then the change in y values, which is y minus 1/2, if I denote the vertical coordinate of that point by y, is going to equal the slope, which is x1, times the change in the x-coordinates. X goes from x1 over 2 at P to x1 over 2 plus x2 over 2 on that long vertical line. So the change in x values is x2 over 2, and I have found the y-coordinate of the center of the circle. It's 1/2 plus x1 times x2 over 2, but we agreed x1 times x2 is the product of the two roots and is therefore equal to the constant c in our quadratic equation. So let's try this. The equation we need to solve is x squared plus 1/2 x minus 1/4 is 0. This is minus b, so b equals negative 1/2. This is c, so c equals negative 1/4. And the algebra I just did said we need to construct a circle whose center is at a value which is the average of the two roots. So since b is equal to negative 1/2, the center has to have x equals minus 1/4. Y, on the other hand, the y-coordinate of the center, we just figured out is 1 plus c over 2. Since c is negative 1/4, this is 3/4 over 2, or 3/8. So we take our compass, we stick the point down to place the center of the circle at x equals negative 1/4, y equals 3/8. We draw the circle so that the point where x equals 0 and y equals 1 is on the circumference. That's in accordance with Euclid's third postulate. And bingo! This circle cuts the x-axis at 2 points, and those are the x-coordinates of solutions of our quadratic equation. That is, those are the x-coordinates of points on our pentagon. So all I do is construct vertical lines at those 2 points. Each gives me 2 vertices on the pentagon. I join them up, and presto, I've done. I've never actually seen this construction published anywhere, but it's clearly the quickest way of constructing a pentagon. Richmond is an English mathematician from the late 19th century. He is most famous for his construction of the regular 17-sided polygon, but a similar strategy can be used to construct the regular pentagon, and it makes very clever use of trigonometric identities. So here's our equation again, and now I say I can basically eliminate one variable if I call the first root tangent of beta over 2 and the second root negative cotangent beta over 2. Then when I multiply x1 times x2, no matter what the value of beta may be, my numerator is tangent times cotangent, which is 1, and therefore the product of these two things is negative 1/4. So that means I only have to figure out how to choose beta so that the coefficient of x is equal to 1/2. That is, so that the sum of these two roots is negative 1/2. So I need x1 plus x2 equals negative 1/2. Now, it's easy to think that there's no point in memorizing lots of trig identities because you can always work them out when you need them. But here's a counterexample. If you happen to know that cotangent 2 beta is 1/2 cotangent beta minus tan beta, and I confess I've never met anyone who knew this unless they learned it from me in learning this construction. On the other hand, if you happen to do that, then you can say this quantity is negative cotangent 2 beta, and so the negative cotangent of 2 beta has to be minus 1/2, or alternatively, the tangent of 2 beta has to equal 2. And that's an equation that lets us construct beta very quickly. So we need an angle whose tangent is 2 beta. That's easily done. In our circle, the radius has length 1. If we bisect it, we get a side of length 1/2, and the tangent of this angle is equal to 1 divided by 1/2, or 2. So we've constructed 2 beta simply by bisecting one side of this circle. To construct beta, we bisect the angle, one of the earliest constructions in Euclid Book 1, and the place where that bisector intersects the x-axis is 1/2, this length, times the tangent of 2 beta. That's our root x1. If we construct a perpendicular to that bisector, we can also construct the point negative 1/2 times the cotangent of beta. Bingo! We draw the 2 vertical lines, and we completed the construction in exactly the same way. And I think in terms of number of uses of the compass required, this is probably the most efficient construction of the regular pentagon ever devised. But you say, can't Euclid do this too? Well, yes, he can. And his construction proceeds in 3 steps. If you look back to Book 2, Proposition 11, Euclid divides a segment into 2 pieces so that the product of the whole and the smaller part, which he makes into the area of a rectangle is equal to the square of the other part. Now, here is the diagram from that, and in fact, the side that Euclid subdivides, come on, come back to life, there you are. Euclid divides this horizontal line into two pieces, which are y and 1 minus y. And what he says is that the whole, which is 1, times the shorter part, which is 1 minus y, is equal to the square on the larger part, or 1 minus y equals y squared, or if you prefer, y squared plus y minus 1 equals 0. So there are, in fact, in this diagram, two lines that have been divided in the golden ratio, this one and the horizontal one. Take your choice. Either one will work. Now, says Euclid in Book 4, we know how to divide a segment so that it has two pieces, one of length y, one of length 1, with the property that y squared plus y minus 1 equals 0. So here is a line thus subdivided. Now, we construct an isosceles triangle whose base is the piece of side y and whose two other sides have length 1. And now, if you look at these in terms of similar triangles, which Euclid doesn't have available to him in Book 3, but which we certainly know about, we say, okay, we have two triangles, ABD and BCD. They have an angle beta in common. They're both isosceles, and any two isosceles triangles with equal base angles are similar to one another. And therefore, ratio of side to base in the red triangle, 1 over y, is equal to ratio of side to base in the larger triangle, ABD, which is y plus 1 over 1. And when we multiply this out, we get y times y plus 1 equals 1. Now, the important thing about these triangles is the following. Here is another isosceles triangle. These two sides are equal. This angle is alpha. The triangle is isosceles, so this angle is also alpha. And here is an exterior angle of that triangle, beta. But Euclid proves that any exterior angle of a triangle is equal to the sum of the two opposite interior triangles, and therefore beta is equal to 2 alpha. And we have constructed an isosceles triangle where the base angles beta are both equal to 2 times the remaining angle. If you want to express this in degrees, beta is 72 degrees, alpha is 36 degrees, and of course 72 degrees is exactly the angle we need in order to construct a pentagon. So Euclid has already shown us, when he gets to this construction, how to inscribe a triangle in a given circle. So he inscribes in a circle a triangle for which the base angles are equal to twice the remaining angle. Now, beta is equal to 2 alpha. So if you bisect beta, you're going to get alpha here, you're going to get alpha there, and you are going to get over here another vertex of your pentagon. Similarly, if you bisect the angle at C and find where that intersects the circle, you get the fifth vertex of the pentagon. If you actually draw all the lines in the triangle, the bisecting lines, and the line that joins them, you have constructed a pentagram. If you just join up the vertices, as I've done in red, you have a regular pentagon. And that's Euclid's construction of the pentagon. Well, this looks good, doesn't it? Let's see if we can do the same thing with the heptagon. So here is a diagram showing a regular heptagon. And by now we figured out that the best approach is to use the angle to there and the angle to there. In other words, where we used 2 theta and 3 theta before, we now use 3 theta and 4 theta. And we say this angle theta satisfies the equation cosine 4 theta minus cosine 3 theta equals 0. We drag out our trig identities. We worked this one out earlier. And since we know the formula for cosine 2 theta, it's 2 cos squared theta minus 1, cos 4 theta isn't hard to get at all. It is twice the square of cosine 2 theta minus 1. Here it is in terms of powers of cosine theta. We set cosine 4 theta equal to cosine 3 theta, combine all the terms, and we get this 4th degree equation. But again, theta equals 0 is a solution. Cosine theta minus 1 is a factor. So we get a cubic equation from the heptagon. In this case, it is most convenient to introduce a new variable y equal to 2 cos theta. And we have reduced the problem of constructing a heptagon to the problem of solving this specific cubic equation. Unfortunately, while you can solve an arbitrary quadratic equation with compass and straight edge, there is no Euclidean construction that solves a cubic equation. However, as you will learn in the next and final video, if you're willing to cheat a little bit by putting 2 marks on your straight edge, then you can solve cubic equations, and I will show you in the final video next time how to construct a regular heptagon by using a compass and an unmarked straight edge.